later. So today's agenda, we're going to talk about electrical potential some more and actually start to expand that into more details about capacitance, which overflows with the PhET kind of inquiry activity that I had you working on. And then we're going to practice with an FRQ from your textbook and also watch a daily video. I don't expect that we'll get to that second FRQ today. That'll probably come next week. I have them both ready just in case, but I don't think we'll probably get there. If there's just a small bit of time left at the end, rather than doing that, we'll probably just give you a little time to wrap up that exercise and get that turned in today, since today's the due date for that. So that's the agenda. Let's go ahead and start with the daily video, and then we will look at an FRQ and then take some notes. We'll get to this first. Actually, let me just make sure I've got share sound. I don't think I remember to share sound the other day, but you said you could hear it, so it must have just been being picked up by the microphone. Okay, I'm not sure. Yeah. Usually if you click share sound, it comes through nice and loud, but there we go. I like the fact that this TV has a computer built into it, so it works nice for touch. It didn't request it. That must have hit something different. That's trying a different route. I don't want to create it on the password right now. I was just saying I like the fact that the computer is built in, but it does go really slow when there's multiple things going on, like recording and Zoom, and it really makes things creep. All right, it's gonna work now or not? Why is it making me do this? You didn't request a temporary password to reset your account. You received. Oh, so you have to change it every 12 months, and right now they're making you do it. Okay, well, we'll skip the video then, and we'll look at it another time, because I don't want to mess with that right now. So let's just go on with the FRQ instead. Or maybe while you're working on that, I can work on this in the background, try to get that figured out. So for the FRQ, this was actually from your textbook, but they obviously have some of the same writers that write the tests. And this one is similar to the one we did before, but with a slightly different twist and definitely some different kind of questions. Now, just to save paper, I've actually printed the scoring guide with the question. So, because the question's only this. It's just one side of one paper, but the scoring guide's 3 pages, and I didn't want to have to waste a whole other sheet of paper per student. So the only thing you're answering is just what's on the very front of the first page. And then for, I guess it's just Ethan, everybody else made it. So for Ethan, if you're watching the video, this is on Unit 3 on Axis. So you can find this textbook Chapter 4 FRQ. This one is a 20-minute FRQ, so we'll give you about 20 minutes. So we'll go to about 12:50, and then we'll have you check it and discuss it. We got a negative test or something, we have to stay on quarantine very long. Oh, okay. They just would go, they just being cautious. Yeah. All right, we'll go to about 12:50. Go ahead and look at the scoring guidelines and check and see how you think you would score based on your results if you haven't already had a chance to do that. While you're looking that over, you can feel free to discuss it as well. And then I'll make a couple comments and just see if there's any questions. But while you're looking that over, the answers to the one we did the last class printed finally. So since I have them, I'll go ahead and give them to you. I don't know if you want to keep it with the other one or not, but just in case it's helpful. All right, so as you look over the first part A, any questions about the drawing of the arrows? They didn't give you a lot of space to draw them with clear, relevant lengths, but hopefully, does it make sense why they are the lengths that they are? Any questions about that at all? All right, for part B, what was the wording then on the question? I should have tucked that away in. Describe the approximate location where it would be 0. So it's going to be somewhere between the 0 and halfway between, so in here somewhere. And then they give some rationale, thinking through the superposition of the fields, that between the two positives is where they'll cancel. But then you've got the impact of this negative charge that's attracting them, so it's going to end up being somewhere to the right of that. So just recognizing that, and let's see, correctly, a lot of strings field due to each charge. Oh yeah, just somewhere in your explanation, basically commenting on the fact that it's relative both to the magnitude and the position, but the position is a quadratic relationship, not linear. So anything you want to ask about B? All right, and then for C, they do give you the example paragraph. And then for C, asking us to determine the magnitude of the X and Y components. And so they draw a little diagram here on the example to show you that the Y component is just this, because the Y components of these two cancel. Since they're equal charge and equidistant from that point, the Y components of E1 and E3 cancel. But E2, that Q2 does create a field upward. So that's the only Y component. And then the E1, E3 fields would have equivalent X components. So that's why we end up seeing that it gets doubled down here when you look at their steps. That's where this 2 comes from. And since it's X components, we're looking for the cosine, the horizontal component there. So any questions about the deriving of the equations for Y and X components? Okay. All right, so we'll keep practicing a variety of different kinds of questions. This one I thought was interesting because it was actually from your textbook. And I did go ahead and get this thing squared away while you were working. So we'll watch the video now. Let me scroll it back here a little bit. And hopefully this will work.
From Glastonbury High School in Glastonbury, Connecticut. Today we're going to be talking about when we have uniform fields. When I have a uniform field, we get equally spaced isolines, and that happens in several different ways. We can use topographic maps of gravitational field to compare those to the isoline maps of electric potential. So let's take a look at the gravitational example first. Let's say I have 4 locations near the surface of the Earth. We did this problem before, do you remember it? If you haven't watched the video on isolines, go back and watch. In any case, the magnitude of gravitational field at each location is 9.8 newtons per coulomb pointed towards the center of the Earth for all of these different points because they're sufficiently near the surface of the Earth. We can use gravitational field vectors that all point down. And so if I were standing and looking out at the horizon on Earth, I could imagine these gravitational field vectors uniformly all pointing down. And there's our person for perspective, so that you know you're looking out at the horizon and not down at the surface of the Earth from this point. Near the surface of the Earth, we have equally spaced isolines. The gravitational isolines represent lines of equal altitude. Anywhere along that line would have a height of 10 meters and would have the same gravitational potential energy per unit mass. So now let's use this topographical maps and isoline notation to think about electric fields. The electric field can be uniform in a couple different ways. In the last video, we talked about how between the plates of a parallel plate capacitor, you get this uniform electric field, where just like in the gravitational pictures, all of the field vectors are pointing down with negligible end effects.
I want to make a
That
comment
means
about
between the
that.
plates of a parallel plate capacitor, the field vectors are pointing down with negligible end effects. That means between the plates of a parallel, all of the field vectors are pointing down.
There you go. Guess we just have to wait a while. So she talked about end effects, and today in our lesson we're going to talk about capacitance theory, where we're not looking at a real capacitor, but the idea of how a capacitor works. And then when we talk about capacitance theory, we consider these plates to be infinite. So that's the basic lesson for today. But in this video, she talked about end effects. And so hopefully you can see, and you may even have experienced this when you were doing your activity a couple weeks ago. But see how these kind of curve on the outer edge, whereas they're straight in the middle. If you have a true capacitor with an end, as you get to the end, you start to see a curving out of that force based on some of the repulsions that exist. And so, or not force, but field. And so that those curved end effects occur. And I'm mainly highlighting that because one of the other FRQs we're going to practice next week actually asks you to draw that and represent the fact that that will curve on the edges of a capacitor. But it isn't highlighted in our notes very thoroughly, and it's not highlighted in the book very thoroughly, so I just want to make sure. I thought she did a nice job of mentioning it, but she didn't really explain it, so just want to make sure that it didn't pass by. So when there is an edge to the capacitor, it's not an infinite plate of charges, you see some curvature outward on those edges. We call that end effects.
With negligible end effects. That means between the plates of a parallel plate capacitor, you have equally spaced isolines. In this case, I did 10-volt increments. And if we see the 10-volt increments approximately, we can see that they're evenly spaced for the points in the center of the capacitor. But what if you removed one of the plates? Like when we're dealing with the surface of the Earth, it's just one big Earth. If I remove the top plate, does it still have an electric field that's uniform? The answer is yes. If you are sufficiently near a large plate of charge, then you can still have equally spaced isolines. Now, the reason this picture is a little bit grainy is because in order to see this effect, you need to either be with a sufficiently large plate, or sufficiently close to the surface of a small plate. Hence the zooming and the fuzziness in this picture here. In this case, the isolines are 25 volts apart, and they're mostly equal. The closer you get in this scenario to the plates, the more equally spaced they will be.
It's a bit analogous to gravity. We talk about gravity being constant, 9.8, anywhere near, right? for the gravitational field of Earth. But we do know if you get sufficiently far away, then that doesn't follow through. So if you're on the International Space Station, it's no longer 9.8, right? So as long as you're near, it's not the same exact thing, but it is a field relationship, and there's a lot of analogies between the two. And so as long as you're near this very large plate, you're going to have that same relationship.
And in the last example, what if instead of a flat plate, it was like being near a very large sphere, like being near the surface of the Earth, because the radius of the Earth is large enough to aim net gravitational field downward. So in the same way, if I take a sphere of charge, there's my sphere, and I take charges along the outside, I have a mostly uniform electric field, and sufficiently close enough, it would be uniform, meaning all the electric field would point in the same direction and have the same magnitude. That also means that close to this sufficiently large sphere would have equally spaced isolines. So let us practice this skill. Pause the video, read closely, and let me know what you think.
So which of the following best describes the shape of the isolines of potential for the gravitational field in and the electric field in these regions? Maybe just a little bit of typo there. So isolines are straight vertical lines for both gravity and electric fields. Isolines are straight horizontal lines for both gravitational and electric fields. Gravitational isolines are straight while electric isolines are curved. Gravitational isolines are curved I think there's a lot of typos in this one, while electric isolines are straight. Which one of those is correct? Have a whole variety of different representations, but I think you're all saying the same thing, or most of you. So let's hear it.
All right, here's what I'm thinking. And in this case, they're horizontal lines. Isolines on Earth would be our isolines of equal gravitational potential energy, or equal altitude. So in this case, they'll be horizontal. The fields, however, would be vertical. So in this case, the best possible answer would be B. The isolines are straight horizontal lines for both the electric
And
and
don't forget that the
gravitational
field, she
field.
mentioned that their field lines are vertical. Remember, they're always perpendicular to the isolines.
Okay, so let's try another one. Let's say this picture shows a region of uniform gravitational field near the surface of the Earth. Maybe this is outside of my house. We've got vertical gravitational field vectors pointing down towards the center of the Earth, all with a magnitude of 9.8 newtons per kilogram. And these dashed horizontal lines represent the lines of equal altitude. So if I use the same diagram, but instead said it represents the electric field near a large negative plate, now what would the lines represent?
So if this is now an electric field and it's near a large negative plate, does that mean A, the field vectors point towards the negative plate and the dashed lines are lines of equal charge? Is it B, the field vectors point away from the negative plate and the dashed lines are lines of equal charge? Is it C, the field vectors point toward the negative plate and the dashed lines are lines of equal electric potential? Or is it D, the field vectors point away from the negative plate and the dashed lines are lines of equal electric potential? What do you think? Again, it's interesting. There's sign language mixed with like the shape of the letter, mixed with the numerical representation, but I think you're pretty much all saying the same thing.
Pause the video. Okay, here's what super tricky. I think a lot of people would look at A and say, oh, lines of equal charge, that sounds right. But no, my friends, we're talking about lines of equal electric potential. An isoline is a line of equal electric potential. So I should be picking C. The field vectors point away from positive charges and therefore towards the negative charge. The field vectors are all pointing down towards the negative plate, and so my dashed horizontal lines are my lines of equal electric potential, not equal electric charge. Takeaway is then that near the surface of the Earth, our gravitational field is represented by vertical vectors that all point down. and that their isolines are horizontal lines of equal altitude. All right, we got this. The electrical equivalent then is that we can have a uniform field between the plates of a parallel capacitor. That's one. When sufficiently close to a large plate, or sufficiently close to a very large charged sphere, like if you were sufficiently close to a Van de Graaff generator. So in any of those three cases, it's depicted by equal isolines, equally spaced. And in this picture, I see that I have negative isolines, indicating I must be near a negative Van de Graaff generator. That's all for now, folks. Join Mrs. Rednick next time for conservation of energy. Bye now.
All right, so we've got the FRQ, we've got the video. Now let's get into some more notes. So this is where we're gonna, like I said, start to cross even more fully into Unit 3 with circuits and specifically the concept of capacitance. So, but we're gonna approach it from electric potential since that's what we were just studying. There's gonna be a bunch of reading, so I'll get us started, but then I think we'll just kind of move around the room because waiting on volunteers will take too long, and if you all just kind of read in order, it'll go much quicker and we'll be more efficient with our time. So I'll read this one. Up until now, we've dealt with electric fields and potentials due to individual charges. However, a more practical application of this is when you have configurations of a massive amount of charges. So we've mostly been focused on point charges, one of them, two of them, three of them, four of them at most. Now we're saying, well, in terms of practical circuitry, it's not going to be individual charges, it's going to be plates that become charged. All right, that's the basic principle here. Jackie, would you read this one for us?
Let's begin by examining two infinite planes of charge that are separated by a small distance. The planes have equal amounts of charge, with one plate being charged positively and other negatively. Diagram to the left responses to infinite plates.
So obviously they can't show infinity exactly, but they're just trying to help you see if this kept going and going and imagining it that way. All right, Tiger, got this one?
This is an idealized picture of a critical electric circuit element, the capacitor. We are now going to work with electric field, electric potential energy, and electric potential to explain the theory of the capacitor.
And Carter.
By applying Gauss's law from AP Physics C, it is found that the strength of the electric field lines will be uniform between the planes. It will have the same magnitude and direction everywhere between planes, and the electric field outside the two planes will equal zero.
All right, you don't need to know about Gauss's law, but if you're curious, it is in your textbook. So you can look that up if you're curious to know about that, but it's not an AP2 topic. All right, John?
Point charges have a non-uniform field strength since the field weakens the distance. Only some equations we have learned will apply to uniform electric fields. Uniform means constant magnitude and direction.
All right, there is a demo, but you need a special piece of equipment to do it, and we don't have that piece of equipment, so. All right, so based on the very brief intro, if the strength of the electric field at point A is 5,000 newtons per coulomb, what is the strength of the electric field at point B? If you were paying close attention as we read through that, hopefully you caught on that inside the field is going to be constant. So it would also be 5,000 newtons per coulomb. All right. If the strength of the electric field at point A is 5,000 newtons per coulomb, what's the strength of the electric field at point B? Again, if you paid attention as we were reading through that, you know that outside the field it's going to be 0, which is A. All right, just a couple quick, making sure you were paying attention. All right, and Jason.
For the parallel planes, the electric field is generated by the separation of charges. The field lines originating on the positive charges and terminating on the negative charges. The difference in electric potentials or voltage is responsible for electric field.
All right, so the electric field is caused by that difference in potential, but it will always radiate, just like when we drew fields for point charges, from the positive to the negative. Okay, so similar patterns. All right, Sean?
Energy is being put into the parallel plane charge system when the positive charge moves in the opposite direction of the electric field, or when a negative charge moves in the same direction of the electric field. And in this example, positive work is being done by the external force. And since the positive charge is moving opposite the electric field, negative work is being done by the
All right, so you have to think about which is doing the work. Is it the external force? Is it the field itself? Would that positive charge naturally move in the direction they're showing in the diagram? No, it would have to be going against the repulsion of the positive plate, right? So work has to be being done by some external force, which means that force and the direction of the movement of the charge have to be in line, right? And so that's going to be considered positive work by that external force. The field is trying to push it the other way, so the work that's being done by the field would be considered negative because the charge is moving up, but the field is pushing down, or it's affecting down. All right, John? Oh, sorry, we're not in that row yet. Bob?
If the positive charge was just placed within the field, it will move from top to bottom. In this case, the work done by the electric field is positive. The field is in the same direction as the charge's motion. The potential energy of the system will decrease directly analogous to the movement of a mass within a gravitational field.
So would the positive charge naturally move in this direction? Be repelled by the positive plate, attracted to the negative plate. That is a natural movement. So it says this case, the charge was just placed within the field. So you have to read the questions carefully when you're asked things about these capacitance fields. That if it's being moved in the field, that's one kind of question. If it's just being placed in the field, that's another. And so in this case, you're not doing any work. And so in this case, the potential energy of the system will decrease. It's going to just keep moving towards the negative side naturally. In order to store energy in the system, we would have to do work to store it, which means we'd have to push it against the natural flow. Okay, so this would have a decrease in potential energy. Just like if you have an object up on the top shelf and you move it down to a lower shelf, it's lost gravitational potential energy. In this case, it's losing electric potential energy because it's flowing in the natural direction, not storing anything up by fighting the repulsions or attractions. Any questions about that? All right. Yeah, Jeff.
So in this scenario, so if the charge is going opposite to the field, it's doing the negative work, or
The force would be doing positive work, but the field would be doing negative work because the charge is going in the opposite direction. So it's just like what we talked about work in AP1, where if the force is this way, but the direction is this way, like a car's rolling down the hill and you're trying to stop it, that's negative work because the force and the direction are opposite each other. But if they're in line with each other, that's positive work. All right. Let's see. I think we're at Ian, right?
Yeah. If there is no other force present, the charge will accelerate to the bottom by Newton's second law. But if we want the charge to move with a constant velocity, then an external force must act opposite to the electric field force. This external force is directed upwards. Since the charge is still moving down but not accelerating, the work done by the external force is negative.
So it's not a true free body diagram because it's not a dot, but it's kind of a sort of a free body diagram here. To have a constant velocity, what has to be true about the acceleration? Zero. And if there's no acceleration, there's no net force, right? So there will be forces, but no net force. And so an electric field is providing a force down and the external force is up, and they must be balanced. And so again, the external force here is actually now pushing with or against the movement. Against. So since the external force is upward, it's doing negative work on the downward moving charge, right? It's just that it's downward moving at a constant velocity. How about the field? What kind of work is the field doing? Positive work, because it's pulling it down and it's moving down. Okay, they're in line with each other. All right, so the external force is doing negative work, but the field itself is doing positive work. there's no acceleration, and there's no net force. All right. So here we have kind of a quick summary. If we have a scenario like this where the object is naturally moving from the repulsion of the positive plate towards the attraction of the negative plate, but it's not accelerating because there's some other external force, then we know that one, the work done by that external force has to be negative because it's in opposite direction. The work done by the field is positive because it's in line with the movement and the force generated by the field are in the same direction. And yet the net force is 0 and the net work is 0 because those forces are equal and opposite. Okay. And then the potential energy of the system, however, is decreasing because we're not going against the natural movement, it's going with it. So we're not storing any energy up because it's actually going the direction it would naturally go. We have to apply a force and do some work against the natural flow in order to store energy in the system. Yeah, Finley?
What kind of thing would like do that? If like the two plates are really close together, you cannot change the charts.
To provide that external force. You would probably have to have some external magnet that would repel it or attract it in the other direction, just between the plates. So you'd have the charges of these plates that are electrically charged, and then maybe some magnet outside above attracting it or below repelling it. Any other questions? All right. And we're going to get into magnetism later, but anytime a charge moves through a field, it also generates its own magnetic field. But we'll get to that in the not unit 3, but unit 4. All right, so what generates the electric field between two parallel oppositely charged plates? Is it that they have the same voltage? Is it they have different voltage on top and bottom? Is it that there are charges moving? Or is it that there are protons moving between the top and bottom plates? What creates the field? I think most people are saying B. The fact that those plates are oppositely charged, that's what creates the field. All right. A positive charge is placed between the two oppositely charged plates as shown below. Which way will the charge move? Okay, another pretty easy one. It's going to be repelled by the top plate, attracted to the bottom plate. It will move down in this configuration. Positive charge moves from the top plate to the bottom plate at a constant velocity. In the configuration below, okay, what is the net work done on this charge? Seeing a variety of answers this time. What is the net work done on this charge? And now I'm starting to see some consistency again. It looked like a few people were saying C, but maybe you were saying 0. I'm not sure. Looked like C for some, but yeah, it is B. The net work is 0 because those forces are equal and opposite if it's going at a constant velocity. Just like in AP1 where constant velocity was a term you want to look for in questions, you want to look for it even in electric field, electric energy, electric force questions. The potential charge moves from top to bottom at a constant velocity in this configuration. What is the work done by the field? Positive, negative, 0, infinite. The field is doing good. Positive work. Almost pretty too far. You got a positive charge moving from the top to the bottom again, constant velocity in the configuration below. What is the work done by the external force? Good. Picking this up well. That's going to be negative. All right. And then, let's see, yep. Where did we leave off? We're at Ian, right? So let's go to Finley.
A positive charge moves from the bottom to the top plate. An external force must act in the upward direction to oppose the electric force which is directed down. The work done by the electric field is negative as the field points in the opposite direction of the charge's motion. The potential energy of the system will increase, analogous to the movement of a mass within a gravitational field.
So if we looked at something from the bottom shelf to the top shelf gravitationally, we've just stored gravitational energy in it because we've worked against gravity, right, to put it up on a higher shelf. Same thing here, it would not naturally move upward in this configuration. So if it does, we've done work. We've provided an external force that can do work. And the field, however, is doing work against it. So the field is negative and the external force is positive. Right, John?
If the charge moves with a constant velocity, then the external force is equal to the electric field force. Since the charge is moving up but not accelerating, the work done by the external force is positive.
All right. And David?
The work done by the external force is positive. The work done by the electric field is negative. The net force and hence the net work is zero. The potential energy of the system increases.
All right, so that's just a quick summary of the opposite scenario where it's not going the natural direction where it's being repelled by the positive and attracted to the negative, but there's some external force that's causing it to go against the natural movement. All right, so a couple quick questions to wrap this up. Positive charge moves from the bottom to the top at a constant velocity in the configuration below. What happens to the electric potential energy of this system? We're storing energy in the system by doing work on it. So it does indeed increase electric potential energy. If a positive charge moves upward in the following diagram with constant velocity, what is the net work done on the charge? Okay, I think we see some agreement here as well. If the net force is zero, then the work done is zero, the net work done. So one's positive, one's negative, they cancel. If the positive charge moves upward in the following diagram, what is the work done on the charge by the field? Work done by the field. Okay, good. Had a few threes mixed in there, but they all started to change. Since the field is down and the movement is up, that's negative work. You can probably predict the next question. If positive charge moves up in the following diagram with constant velocity, what's the work done on the charge by the external force? All right, moving up, force is up, so it is a positive amount of work. All right, and let's see. Let's see how much. This is where I'd planned to stop, but we're done a little bit earlier than I thought. But I think that's still the best stopping point. It'd be another big chunk to get the next section. So I think we will pause there for today. So we got about 20 minutes left. I was thinking it'd probably only be about 10, so you have a little more time than I thought. Which is fine. If you need to finish up still that potential and capacitance PhET activity, that gives you about 20 minutes, almost 17 minutes to, or no, it's 22 minutes. 22 minutes to work on that and get that taken care of. If you're done with it, you can just turn it in. And there's no new assignment right now. We're still just wrapping up this unit.